Hey, section 202. So what I'm going to do is I'm going to go over the three problems of section briefly and discuss the context in which we solve these problems. Quick refresher, when we consider the space of colors or an image, then if we describe the image to be this large block here, then we can decompose this into various pixel objects. In this case, we used 4. And those pixel objects are represented on a real space grid. We index these areas through natural numbers, conceptually. However, there is also a space of colors. The color space is R, G, and B. There are different kinds of color spaces as well, but they all map to the same region in space, right? And the utility of having this color space is that you are able to visualize. So each point in space has a particular red value, a particular green value, and a particular blue value. That's one way of looking at this. The other way of looking at this is that the pixel object is defined to have both a spatial value and an RGB value. The space coordinate need not be one-dimensional. In this picture, I've shown it to be one-dimensional for the purpose of visualization. However, in reality, it could just as well be x, y, and z, in which case we'd be working in a coordinate space of 6 dimensions. Importantly, all the color which we will ever use come inside this RGB space. One way to consider the RGB space is to think about it literally in terms of a Cartesian frame or an XYZ frame. Note that each one of these axes accept only integer values, that is, all integers from 0 to 255 on each of these axes, and that needs to further be mapped to some real space grid. Okay, we also discussed a little bit the concept of implicit loops, and the discussion mainly was around what this range actually does. This range function generates a list. We noticed that by explicitly using a list, and with the help of that list, we have the understanding that the in operator assigns this value I to the first element and then subsequent elements of this list, which means we can cut out the middleman and directly call on elements of the list itself, right? We're going to use this approach when we deal with the Narok filter problem. So what is the Narok filter problem? The filter problem is we have Simba, who's fantastic, and we would like to change parts of Simba's look. Now, we know that a pixel is represented by 3 integers. We just discussed this from 0 to 255. The average is defined. Now remember, the average could have been defined in 2 ways. We have 5 variables, 2 in space, 3 in color. The average could have been defined in terms of x plus y by 2, but that's not the average. The pixel average is defined by the color space average, the RGB sum. So r plus g plus b by 3. Okay. There is another operation which we're doing. It's called thresholding. We're mapping a continuous set of values into a smaller set of values by thresholding them, which is to say we replace them. Now, the thresholding operation is similar in style to one where we take an input and we force it to become 1 or 0. In some sense, it's similar to the on-off switch, only here the on-off values are the average values. Okay? This will become clearer as we go along. Okay, so there's a tip. We may or may not follow that tip. Since we already covered this in section, I'm going to run through this very quickly. Simply because we would like to get the function average, we can define a helper function called average pixel, right? And what will average pixel take? It will take a pixel. I'm going to write it as short form px, and it will return, so we will return, this is actually a fairly small function really. We could have kept it inline as well, but for legibility purposes we'll extract this. Okay. Alright, we're going to also do a little bit of an extension to this, so don't be too surprised. And the extension is something which maybe, okay, let's first start by working through this logic. So we would like to get each pixel. So for pixel in image, we have loaded the image, and what we want to do with it. Well, first we should check whether we're actually getting what we expect, right? I'm in no hurry at all, but nevertheless, it is 2:30 in the morning. So the print statement is telling us that we have our G and B values. We know from the documentation, we will be referring to the documentation many times. From the documentation, we know that we have the accessibility in the form of these attributes. We're not really going to talk about classes here, but suffice to say that we can access the values in this manner. And what we want to do is we want to calculate the average pixel for each of these. So we'll say AVG is AVGP pix, and we will get back the average. Right, there we go. Now at this stage, let's see what happens if we continue here. We would like to threshold this. In fact, we could further simplify this, and well, let's write this right here. So if the average of the pixel is greater than 153, right, then pix.red is equal to pix.blue. Here we're using the fact that we can do multiple assignments in one line. We didn't have to do it this way at all, but we are. So it's basically the association goes from right to left, so or basically left to right in this case. So red is blue is green, which is average. Okay. To be very explicit about what we're doing, we're also going to set this. This is actually not required. The reason why we're setting this is, we can talk about that later. So set pixel. Actually, let's not even bother with that. So we are changing these values in place. We have a pixel. We're changing the value in place. Let us see if this has worked out for us. Let's use image show. Note that there are a couple of things which we've already done, even though this might seem like a quick program to write. There are a lot of concepts here. It's your first time working with images. This works, however, I assert that there's a problem, and that comes from the definition. It's not a problem of the program, but it is a problem of the way we have implemented this. I mentioned before that the color space is formed of integral values, whereas here we're seeing a lot of floats. Because this is a conceptual mistake, I would suggest very strongly that you fix this. If only because the computer will never catch these sort of errors, so it's very important for us as a user to deal with these. Now, a couple of things about this. I prefer the explicit typecast, so that's what I'm going to use. You may see the integral division, which I'm not a fan of, so we will not see it again, right? And that's it. This is Narok. This is the Narok filter. Let's move on smoothly to the next one. Yeah. Trim crop. What is the operation which we do when we do trim crop? Right now we were considering each pixel, we were going over each pixel, and we were dealing with each pixel individually. We were working only in the color space. We did not need X and Y at all. Right now, the operation which we're going to make next is the operation of truncation. We are going to make a smaller image and then populate that smaller image with elements of the larger image if it satisfies the constraints. That sounds like a lot of mathematical stuff, but it's really not that bad. Let's see how that works. What do we use to make this tractable for us? Well, we have two accessors, two global accessors. We can access the width and the height of an image. Furthermore, we can create a blank canvas. A blank canvas is created through this syntax here, right here. We are going to copy and paste this because that's okay. In terms of getting and setting pixels by value, we can get a pixel in this manner and we can set a pixel in this manner. We will be using both, perhaps. Let's see. Alright, so let's move right into trim image. We have a nice little carol. One of the first things I like to do with the code is make sure it at least runs. Okay, and in order to do that, what we're going to have to do is we're going to have to create a simple image object. And actually, right in the beginning, we can return the original image just to ensure that this code will not crash. Just like that. It's not actually going to do very much, but okay. Right now we have problem. Problem is we need to create a blank canvas, and that is not the way to create a blank canvas. The way to create a blank canvas, which is what I copied out there, is that we call the blank functionality, and this returns an object of type simple image. Okay. In fact, we can even return this blank image. The blank image looks blank. Well, unsurprisingly, it is an unpopulated canvas, right? Now we're going to solve this in main itself. In this trim crop image function itself. In order to do this, first of all, we need to calculate the appropriate height and the appropriate width. The appropriate width is, note that the trimming which we want to do is on all four sides. It is symmetric, which means that the width is reduced twofold from the original width, right? I'm going to define these helper functions not because they need to be defined, but because that's the logic behind helper functions. They become slightly shorter than writing the entire code and much more readable. So I would suggest strongly that you all also use these helper variables, helper functions whenever you feel like. Okay, so the new width is the old width minus 2 times the trim size. Yeah, we can agree with that. By the way, pause the video before I move to the next step, in case you're wondering how, and you should be wondering how, we're planning to apply this mathematical constraint which we discussed previously. So the old height is like so, and the new height is, I'm going to call it NH because I'm not going to type that much. In fact, I'm going to call this NW, and I'm going to call this OW and OH because I like short variable names. Your variable name should be descriptive, not like mine, but we're going to take that for now. It's fine. So we now have a new canvas and a new, this is the appropriate size. However, what about actually bringing in what we'd like to bring in? So how should we do this? Should we access every pixel again? Absolutely. For pixel in n image, note that we are now looping over n image. Why are we looping over an image, you might ask? We actually don't need to. Let's do a simpler version where we're looping over the original image. It is original img. Okay. So now we have a pixel here. We would like to test certain things about this pixel. What are we going to test? We're going to test its x value. For simplicity, we're going to rename it as x. We're going to rename y as px dot y, right? This is the xy pair which we have. What is the constraint which we apply? Think about this. So pause the video and please think about this. Feel free to draw out what you need to draw out as well. Right, so thank you for pausing the video and thinking about this. The idea is we need to be careful to ensure that the trim size is not greater than x. In fact, I'm going to keep the original names because it's clearer. So if the trim size is, so the pixel needs to be between trim size and the width minus trim size, yeah? So we have OW minus trim size. If you're wondering, so this basically is the reason why we have 2 times here. I am going to use the line continuation character here. It allows me to write cleaner code. because it allows me to break this large logical statement into 2 lines and therefore makes it much more readable, hopefully. This will now be the height and minus trim size, right? Alright, so what happens if this large logical statement is true? If the large logical statement is true, then we say that n image, new image, by convention, by Python convention, we would have written this as new underscore image. I'm keeping it very short, so I'm not going to do that. We'll use the set pixel helper function. How do I know there's a set pixel worker function, helper function? I looked it up previously, remember? Right here. Alright, so we have the x value. Do we have the x value really? Remember, we're looping over the original image, but we're setting values which are going to be smaller. In fact, just to make sure everyone's on the same page on this, I'm going to let this error out and see how we feel about that. Error. Now, why is this an error? It's an error because we are accessing a region which does not exist. How do we fix this? Well, actually, the new image size is reduced by trim size, yeah? So we will reduce this by trim size. And we'll do a similar reduction in the y value. Let's take a look. We have cropped our Carol, which is fantastic. You guys were great. Let us move on swiftly and decisively to the border edition. Okay, conceptually, what's going on with the border edition? The border edition is the exact replica of what we just did, only now we need to make sure that we're making the larger image, right? Other than that, there's not very much going on here. However, we're basically, so this is a very important operation. It's basically an embedding. We want to embed this guy into the other guy, which means conceptually we need to know whether we're in a border, right? We want to break this up a little bit more than the last one, just, you know, to shake things up. We need to recognize a border. So what is the condition for being in a border? First of all, as I did in the last one, I would like to return something which makes this code run. For now, I'm going to go with original image, just because. Alright, so we have Simba. Simba is amazing. Simba is really neat. Okay, so we would like to know if we are in a border. So is border pixel, how do we know if it's a border pixel? Well, we would like to know the x value, the y value. So we need to know, note that this is a hypothetical pixel. We don't actually need to pass it a pixel. All we need is the hypothetical x and y value, the border, the real border size, the b size as it were, border size, and perhaps most importantly we need the original height and width of the image. I'm going to pass it the whole damn image. Why? Because we have a simple way of getting the original image width out. Original image height out. Okay, so what makes a border? Let's think about that for a few seconds. Pause the video, think about that for a little while, because it is something to be thought about. It's good practice. Think about what we're actually doing here. We take one image, we're embedding it. What are the boundaries? If this feels more like math and applied mathematics than programming, well, sadly, that is pretty true, really. I mean, you're absolutely right. But it's still a useful thing to do. Such is life. Okay, so we have two boundations on the x, which is to say if the x-axis, if x is less than the boundary size, right? Because remember, the new image is, what is it? The new image is larger this time. So if it's smaller than the border size, then we say, well, that's going to be, so why do we care about whether it's a black pixel or not? Well, if it's a black pixel, if it's a border pixel, we need to set the color. We don't know how to extrapolate the colors of the image yet. You can think about that for a project, actually. But what we do know is what logical operator should we do? If it's less than the border, that's this part here. Or what's the or? What can we do for the or? So less than the border, this much border size, and if it's greater than here, right? What is the definition of here? Well, the definition of here is the border plus the entire image, right? So we use or. X is greater than, I'm going to put equal because actually just strictly greater than, I want all of Simba's goodness to be captured. Or yeah, so or greater than this plus the border size. Okay, then we return true. Similarly, the exact same condition is going to apply on y, to the point that I could have used the continuation character and written it here, which is actually what I'm planning on doing right now. Y less than border size, or y. Although I would rather not do that, because here this might be a little confusing otherwise. So we would like to clarify the x and y ones separately. We could wrap them, but then we'd also need to be careful to put them in enclosed brackets to ensure that the logical ordering is correct. So instead of getting into that right now, remember Boolean values in Python have to be caps locked like that, else return false. Also remember, we could have used the two ifs, but it's nicer to use an elif. Okay, this is a style called early return, which previously used to be thought kind of a not so great practice, but nowadays it's very much accepted, and I would suggest it in most cases. Okay, what's the logic which we are applying here? Well, similar to the old one, right? Very similar, to the point that we might as well copy it, but we're not going to do that because... So, the original image width plus what? Plus the border size times 2, right? That's the new width. The new height is almost exactly the same, only now we're working with height. And finally, we would like to get a new image. Simple image, blank, W and H. Okay, the paradigm we're going to be using this time, we're not going to be looping over the pixels. Why aren't we looping over the pixels? Because, this is very important, think this through, okay? When we loop over this one at a time, then the operation which we're really doing is we're taking the product of, let's suppose we have two sets of numbers. Okay, let's just call this x, let's just call the other guy y, just for fun. If we loop over these one time, then we can get pairs, but single pairs. Just to say, we can get 2 and 5, 1 and 4, 3 and 6. If we wanted to get the so-called, like this product, I believe it's the Cartesian product or the Hadamard product, depending on whether you're coming from a physics or maths background. If we wanted this, then what that means is you take 1 and you multiply it by, and you return 1 4, you return 1 5, and you return 1 6. Then you do the same for 2. You return 2 4, 2 5, 2 6, 3 4, 3 5, 3 6. All of them. Then you need another loop. We need that loop. We can't go pixel by pixel like we did in the last one, because then we're not going to access all of these guys. Okay, because we're sort of saying for each row, all of these pixels, for each, etc. So the long and short of this is we are going to now range over the width and height. Okay, let's see how that works out for us. we need a pixel to work with, right? That's kind of what we're thinking of, right? So we do an image get pixel. The signature for get pixel is x, y, border size. This is something which we need to remember or look up. Original image. My bad, I mixed them up. So to get the pixel, we only need two things, x and y. To call our function, if border pixel, or if is border. Now is border takes a little bit more, it takes x, y, and these guys. No wonder that isn't at the top of my mind. We just wrote this function. If this returns true, then what do we say? Then we say that, hey, we have reached a border and we're going to set the current pixel to black. If it's not true, then we need to copy over the image. How do we copy over the image? We do an image and set pixel x, y, the original image. I didn't need to do it this way, but I am, so that's fine. White space in Python is surprisingly forgiving at some points. So like here it doesn't care, and I'm going to do that right here because I don't want to write more. So we need a pixel. However, once again, to get the right one, we need to provide the right spacing. Because similar to the last time, only now we need to remove these because we're looping over the natural index of the larger image. So we need to remove the border, right? Let's see if this is going to give us what we want. No, it's not. Why is it not giving us what we want? Because I was lazy and I typed in a line continuation without, yeah. Okay. That's on me. Don't worry about that. Won't take long. Yeah, I should. This stage, if you're wondering, maybe it would have been faster for me to have just written out the variable, then the answer is yes, you're absolutely right. I should have perhaps just written out the variable. And I am, in fact, going to do just that. Okay. OPX. And what is OPX? OPX is original image get pixel x minus border size y minus border size, right? Okay. Let's see if this gives us what we want. No, because we called the wrong function. It's is border pixel, not is border, which won't make much sense as a function name. Okay, so now we have a separate problem, which is that we are at a bad coordinate. Now, pause the video and think about this a little bit. This is an important problem. What is it telling us? It's telling us that it's trying to get this pixel 0, 2 to 2. Now, first of all, convince yourself that the image does not actually have this pixel available. There are two ways to convince yourself of this. You can remember, if you do, it's great, that the indexing goes from 0 to the last one non-exclusive. But if you don't, like me, I suggest just make sure that it's really true. So the last pixel, last large pixel is actually this guy. Yeah. So now that we know the problem, then the solution will present itself to us. Here we actually need one more line of borders. So all the goodness of Simba is captured between 0 and that, not including this last number, right? So as long as it's equal to this, it needs to be a border pixel, right? Let's see. Beautiful. We have Simba in a beautiful photo frame. I'd suggest improving upon this if you'd like. And yeah, thank you so much. I will see you guys next week. Next week is the last section, last official section. We might have one more. We will discuss this. Okay, yeah, bye. See you.